So, hi. Today I'm going to be talking a bit about what an operating system actually is and just some of the context, some of the history of it, moving into what a more modern operating system looks like and talking a bit about specialist operating systems. So without further ado, let's get started with me properly introducing myself. So, hello, I'm Jacob and I'm a alumni of the University of York. I did a integrated masters in computer science here relatively recently, and actually graduated this year. And I'm therefore a HackSoc alumni now, I guess, though I still hang around it. And I'm now working for a company in York called ETAS, who are a subsidiary Bosch, but they we specialise in embedded software. I'm not here representing them today or anything, so this is nothing to do with them, but I thought it reasonable to mention that, yes, I do work in embedded systems and stuff, which we'll get. So when I talk about it a bit later, I do know a bit of what I'm talking about. I'm sure everyone would trust me to have done my research anyway. So, operating systems. It's a bit of a nebulous term. So, what do people think about when they hear OS? When they hear operating system, what do they think about? I think a lot of people probably go to the graphical operating systems we have everywhere nowadays, so things like Windows, Mac OS, Linux distributions, and on mobile phones, Android and iOS, which are all very ubiquitous nowadays. And these are classic desktop OSs, and a lot of our interactions with them are typically via a user interface, which really hides a lot of what's going on behind the scenes and a lot of what an OS actually does. So things like Windows and Linux, to some, are more associated with the experience of using them and less associated with what's going on behind the scenes. So we're going to talk a bit about that today. And to do that, we need to go back. We need to go back to before operating systems in fact existed. Way back to the first half of the 20th century. So, in the beginning, computers didn't have operating systems. They didn't need them. Your average computer being something very specialised and probably programmed by flipping certain switches on the front of it. So it was not really complex enough to require anything else there. This was the time of bare metal programming, effectively. Things were done directly on the hardware, and you would write everything that got run. As computers moved on, we started to get into the land of mainframes. So that's where you would have a big room filled with a computer, basically. but they were bigger things. They had more processing power, and more importantly, they had more memory to put big programs in. So we started to move to the idea of having your set of programs on punch cards or something, which would be run. And mainframes, etc., were owned by places like universities, etc., which needed to share these resources. They had a big computer, it cost a lot of money. It probably kept costing them a lot of money to maintain it. So they needed to share it, and they needed to build different departments for it, probably. But this was all a very manual process of keeping track of who was using the room when, how much time they'd spent using, say, a wall clock. But as time went on, there started to be supervisory programs or bits of hardware that could help automate this. So things that would take your sets of punch cards and line them up with another set of punch cards from someone else and then run one after the other, and keep all the results separate, that kind of thing. So you would have something watching over them and providing a very, very basic form of multitasking, or a very basic form of multi-user experience. So, as things went on and mainframes got more and more complex, they needed to do more and more stuff. They needed to do proper multi-user systems. So in your older use cases, you just had everything being written by you for your program. So what started to be introduced were sets of shared runtimes, that kind of thing. They could be compiled in with your program. They weren't an OS as such, but they were features we would now associate with an OS. So pre-packaged things like memory management or interrupt handling. The kind of stuff that an OS handles nowadays, but that was all boxed up, ready to use with your application. And those kind of libraries laid the groundwork for the first operating systems, which started to appear on mainframes, and as early as the late 50s. Operating systems were very basic back then, but they started to do some of the things we would associate with operating systems. Most importantly, at least for them at the time, they were allowing multiple users to use the machine at the same time, and well, most importantly for the wallets, the universities, etc., they were keeping track of who was using it. So we have some auditing here, and we have some user management, that kind of thing, but really that's multiprocessing, which is a very important concept nowadays, the ability to run multiple threads of execution at the same time, so multiple users using a machine, that kind of thing. And this actually required changes from the hardware over time to accommodate some of the things that you would need to be able to do to run an operating system. And in the latter half of mainframes, moving into minicomputers, so mainframes but much smaller, these things start to become very common. Some very well-known operating systems popping up, or at least better known than anything that came before them. Things like Unix and VMS. So the early predecessors of some of our modern operating systems, and also things that had a lot of the concepts and could do a lot of the things that our modern operating systems can do. Things like multitasking, which is very important. Working with different processes. I'll get more into that later, but they were providing extra layers on top of what was already in earlier operating systems and producing something that's much more like what we know today. So, as we were getting more and more advanced mini-computers, we also started to see microcomputers appearing, so computers in your home. This would be around the mid-70s to early 80s. And microcomputers were notable because, well, they were small enough and cheap enough to get at home, as I said. But this meant we were kind of back to square one with operating systems, as in, they weren't there anymore. We didn't need them anymore, we were back to a single user on a computer, and that computer was run entirely by that user. What you might end up having is a BASIC interpreter. So BASIC being a primitive programming language, and that would be loaded into some read-only memory inside the computer and would start up with the computer. It's the kind of thing that might happen on a Commodore 64, that kind of thing. And in BASIC, you could do some things that would be reminiscent of operating system tasks nowadays, being able to specify to try and launch something from a particular address, that kind of thing. A very rudimentary form of loading programs. But we still didn't really have an operating system. We started to see things that are, well, you could call them BIOSes, basic input-output systems, but basically hardware abstraction layers. Layers that provided a consistent way for programs to interact with pieces of hardware, where the routines for doing this would be stored inside ROM, but it would still be basically the program doing it, and the program didn't really need to, unless it wanted to, use those. You see this, in fact, on Commodore 64 and computers like it, where you might even run different code on the disk drive that's loading programs to try and make the programs load faster, so-called fast loader programs. So, we've gone back to square one, but as we continue on and microcomputers become more ubiquitous, they make their way into businesses and homes and everywhere, and we start to see operating systems appearing again, modelled after the bigger operating systems that are still around on mainframes and still used in many institutions. So Like I said, a lot of this early stuff was basic input-output systems, hardware abstraction effectively. But then we start to see disk operating systems appearing. So these were operating systems that they didn't come with the computer, and there was typically no long-term storage media inside the computer beyond read-only memory. So there was no hard drive. So they would be loaded off a disk, a floppy disk, and they would be able to load programs off disks, hence disk operating system. So DOS, different forms of DOS like MS-DOS, appeared, and another common disk operating system was CP/M. And these were really the start of modern operating systems on personal computers. Most of the time they were single user affairs, so they would only have a single user running on them at a time, and they would also only be single task affairs or single process affairs, typically. You would have the operating system there, and you'd have the process you were running, and that was it. Now, I think it's important to take an aside here for a second to explain how an operating system typically coexists with programs, which is, as it's described a lot of the time, operating systems seem to be constantly running. And in a way they are. But in your old computer, in your old personal computer that's got a single CPU core, it can't have multiple processes running at the same time. So it can't have the OS running, and it can't have your application running at the same time. Instead, what actually happens is that your program will run, and it will, depending on how it's scheduled, either yield back to the operating system, say, okay, you can run for a bit, which is called cooperative scheduling, or it will be what's called preempted. So typically a periodic interrupt will fire, so a bit in the hardware will call back into the operating system, interrupting what you're doing, and the operating system will get a chance to, if it wants to, start a different program. So that program would, that program would preempt the program that you're using, or it might decide to keep running your program, or it might go do a bit of operating system stuff and then return to your program. So when we think about multitasking and operating systems, and when we think about the operating system always running, it's not that it is in fact always actively running. It is that usually there is something in the background, the data is still there, and there's usually some timer or something that will call back into it at some point. But even on modern operating systems, there are periods of time where, for some, nothing is happening in the operating system. It's all just running your processes. And without some of the hardware features that existed, there would be no real distinction between where the operating system runs and where your user code runs. So with that out of the way, we can get back to talking about the end of our little history lesson. So, as we approach modern times, we start to see the beginnings of what we really associate with operating systems, so graphical user interfaces. And while they're not the real instigator, they are a big driver behind proper multitasking. So being able to run multiple processes at the same time, and some other features that appear to things like memory safety, which is the idea that the memory belonging to one process shouldn't be interfered with by another process. So that's the reason why we can be pretty sure when one program crashes on a modern operating system, it's not going to take down all your other programs. Now, if it does something particularly dramatic, it might, but most of the time it doesn't. And that's because it shouldn't be able to mess with your other program's memory. So, everything it's storing, everything it wants to do, its current state even. So, graphical user interfaces, there were several claims to fame as some of the first ones. The early one being the Xerox Alto, but also, of course, Macintosh operating systems also had very good early user interfaces, and other systems as well. And people do like to fight about what the first graphical operating system was, but it definitely wasn't Windows. So we're now at a point where we're pretty close to a modern OS. We've got our graphical interface, we've got multiple tasks running at the same time, and we've got a few more things that we'll talk about in a sec. So where are we up to? What's going on? So first of all, there is one core thread that goes throughout the whole of the history of operating systems, and one thing they definitely always do, which is resource management. They manage some kind of resource, which is pretty vague, but when you're getting into trying to pin down what makes an operating system, it's pretty hard because there's a lot of different approaches. But they definitely always do manage some kind of resource. More vaguely, what a lot of operating systems do, and what is quite a good base for us to discuss operating systems from, is that they do resource management, but we'll refine that into, particularly, they do memory and virtual memory. So that's things like memory safety and keeping the memory space of one program away from another. They allow you to interact with peripherals, and here I'm also including internal peripherals, devices inside the machine, just anything that isn't the CPU or the memory, basically. They schedule processes, which is a very important part. They manage processes in general, they load them, etc., but they schedule them, which is a massive part of operating systems, particularly in some specialist operating systems. But in general, it's very important that we schedule processes so that they don't hog the CPU. So, for instance, we don't want one process that's really intensely thinking about something to stop every other function on the computer. Because, amongst other things, like the graphical user interface processes would stop. So your nice interface would stop working, but in general it would just not be a very good user experience. And another thing that I haven't really touched on, but that is very important, is the ability for processes to communicate with each other. And you can pretty quickly see why this would be important. So, for instance, you have one process that's producing a stream of audio, such as the driver for the microphone I'm talking into right now. And that stream of audio needs to go to another process, say Audacity that I'm recording this into. And so those two processes need to be able to communicate with each other. In that case, it's going via some kind of sound driver, some kind of sound, however your operating system handles sound. But at its core, that's probably some inter-process communication going on there. And there are many forms of it, things like shared memory and message passing, but it can be a very important part of an operating system, and most modern operating systems it is. Okay, so we know what an operating system really needs to do at its core. How about what an operating system is structured like? Well, the structure of operating systems is interesting because it's widely varied. At its core is a component called the kernel. This is the bit that usually has the highest level of privilege, i.e. the bit that can write directly to hardware, read directly from hardware, that kind of thing. It has control of the memory, it has control of everything. And in security terms, it can do whatever it wants, and it needs to be pretty damn secure because of that, because any program that can get into it can do whatever it wants. But this is the core of your operating system, and it does those things we talked about typically. So it will do resource management, memory allocation, that kind of thing. It will also handle inter-process communication, or at least a basic level of it. You might have higher levels of inter-process communication going on elsewhere, usually built on top of that though. And it does scheduling of tasks, that kind of thing. So we have our kernel, and how much of everything else that a computer does goes in the kernel really defines what type of kernel you have and what type of operating system you have. So some operating systems will have a monolithic kernel, i.e. it will have lots of stuff in it. So that might include drivers for specific devices, so maybe the graphics drivers, the sound drivers, that kind of thing, will all live inside the kernel. So they'll all get high privilege levels and have quite fast access, but the downside is it's extra complexity added to your kernel, and it might be hard to put stuff in and out of the kernel, who knows. On the other hand, you have microkernels, which have basically only those three core things, and maybe a few other little bits, but those core things inside the kernel, and everything else sets out in the same space as your user applications, and needs to call into the operating system that core little bit to be able to do specific things. So it might need to request access to a particular area of memory so that it can do, so it can write to a particular peripheral, it can write to your network card or something. And that would have to go through the operating system, but the driver itself wouldn't be in the operating system. So there are many different architectures for operating systems, for kernels, but modern operating systems tend to be a bit of a mess here, usually because they've been built up over many years and because they're taking the best bits from whatever design they can. So a lot of modern operating systems have what are called hybrid kernels, where some bits are in the user space and some bits live in the kernel space. And you might have some systems which have even weirder architectures. If you want to have a wild ride, go look up Mac OS's architecture and its multiple kernels, and other fun things like that. In general, though, at their core, they're doing a few basic functions with a little bit built on top. They've got those few basic functions we talked about, and on top of that, they will have things like drivers, which may or may not be part of the core kernel, and they will have services like user interfaces, that kind of thing. And all of that is typically referred to as an operating system, though you might get a bit pedantic about which bits of it are and aren't the operating system, and it's kind of hard to draw a line past a certain point. So, is all of that always true? Are all operating systems defined that way? Well, the answer, like the answer to most is that always true questions, is no, it's really not. So there are other specialist operating systems, and we'll touch on them just a little bit here just to give you a taste of some of the other stuff. But in general, the operating systems I've been talking about are desktop or mobile operating systems, and their big thing is that they need to have multiple things running at the same time. They've got to keep the graphic interface running. The user probably wants to do lots of different things. They're quite complicated things, but they don't have some of the more complex requirements that specialist OSs have. For instance, in embedded operating systems, this is operating systems that exist in things like fridges. A big requirement is that they're low power. They don't have much memory, and they keep costs low, that kind of thing, by being small, low memory, low power, that kind of thing. So this used to be the rule of weird and interesting architectures and systems, but more and more you end up with some of the more complicated operating systems making their way in here as it gets cheaper and cheaper to have more complex computers. But one place where it's harder for them to get into is real-time operating systems, which is, you could think of it as a subset of embedded operating systems, but it's the kind of operating system that runs in a car or something like that, or sections of a car. A car has lots of computers in it. And their whole job is really to do things that require a knowledge of real time. So, for instance, if you're braking via a computer, you want the computer that controls your brakes to slam your brakes on in an accident in a certain amount of time. So it has to be able to respond in a certain amount of time, which means you have to have guarantees about how long it takes tasks on that system to run, etc. Or you might have distributed operating systems. So this could be operating systems which need to think of multiple different computers as the same entity, which can be very complex. So you've got things like inter-process communication going on over a network, something like that. So there's a lot more specialized operating systems, but in general, this is the case, that there are different requirements to them, and I'll go slightly more in depth quickly on one of these so you can get an idea about them. So real-time operating systems, like I said, it's the kind of thing that would run in a car, because cars have lots of different computers in them. You might have a plane or something like that as well. They have lots of different computers in them. And so most real-time operating systems end up being also safety critical. Not necessarily, but they're usually something critical, either safety critical or money critical, i.e. if this goes wrong, it will cost us a lot of money. But this means that their core concept and their core design is more based around different priorities. For instance, they need to be reliable. Every time you push the brake pedal, you want the brakes to work. They need to be safe. You want the brakes to work. They need to be secure. You don't want someone outside the car to be able to use your brakes. And depending on how they're made, they need to be somewhat adaptable. And what do I mean by that? So it can mean a lot of different things. Most real-time operating systems actually end up being less adaptable and more generatable. So you end up with a static configuration for your operating system, which means that you can actually feed the configuration in and generate a whole system with all the tasks in it, etc., that are going to run, and compile it all together at the same time. So you don't need to dynamically load anything in, which means that you can swap out what system it's running on pretty easily by just saying to the generator, actually, can you generate me stuff for this system? So it's more that it needs to be compatible with different systems and not that the same thing needs to exactly work on different systems. Unlike desktop OSs, where we expect a program written for one computer with a particular architecture, say one x86 64-bit application to run on another computer running the same OS, we don't necessarily expect that in the embedded world or in the real-time world because things are more tailored to the actual hardware. So, conclusions. What conclusions can we draw from this? Well, I think what you may have got a flavour for is the fact that operating systems kind of evolved out of the need to share resources and keep track of things, obviously, like how much to bill a particular university department, but also to share the computing resources that existed. And that means that resource management is at the core of a lot of them, whether it's sharing them between actual people or sharing them between tasks. And that resource management kind of extends to scheduling. You could think of that as CPU resource management, but scheduling is another core part of them. They need to decide what gets to run when. Now, that's not necessarily the case to a high degree with single process operating systems, because that's only really deciding whether or not the operating system gets to run or that one process. But for more modern operating systems, it's very important that it give everything its fair share of time, so that both the YouTube video you're watching and the game you're playing get the amount of time they need, and one of them doesn't suffer, or something like that. If there was one takeaway from this, I think it's that the core of an operating system is really something very simple. It is that resource management, that scheduling, and the inter-process communication, but that kind of core of resource management. And that really what we see a lot of the time when we interact with an operating system is not really the core of the operating system, but it's all the services that come with an operating system. And at its core, a lot of an operating system's tasks are, when they're working properly, invisible to us. So, what else can I say? I think I would encourage people to go look at specific implementations of operating systems, and I don't mean go look at the code, I just mean go read a bit about how a particular operating system works, because it's usually very interesting. And the history of operating systems is also very interesting. The choices that they make, things like Windows usually making the choice to keep compatibility, even if it costs a lot of time to develop, or how well Mac OS handles changing APIs and completely removing APIs while still not destroying everything for every developer, or at least giving them enough warning. And also changing architecture in an impressive way, usually. And of course, there are many other operating systems you can go look at. Real-time operating systems are a passion of mine, mainly because it's the area I work in a lot with embedded systems. But I think there's some really interesting stuff there, and I would encourage anyone who's at the University of York to take the, if it still exists when you hear this, the modules on real-time systems, because they're very interesting. And yeah, that's about all from me. I'll leave you with some of my related reading and references, and just say thanks again to everyone. If you're watching this live, I think you will be able to come into Discord or something similar to have a chat with me after this, and I'd be very happy to chat about random operating system related stuff, because I barely scratched the surface here. So yeah, thank you very much for having me.